Alright, we begin problem 3. Let's see if I can do this first try. Now, problem 3 states that we have a simple pendulum of mass m whose point of support moves uniformly on a vertical circle with constant frequency. I'm gonna say omega. Okay, so first things first, we draw our picture. So we have our circle and we have our pendulum attached to this circle with a mass m. And let's call the length of the pendulum L. Now, we have to choose a good coordinate axis because, as stated earlier, the most important thing about making these problems simple is choosing a good coordinate axis to describe the system. So I will call this my x position and I will call this my y position. Now let's first begin with x. X is easy. We know that it's moving with constant angular frequency omega. So Uh, from the unit circle, we know that our x-axis on a circle is always correspondent to the cosine of whatever angle we have. So we can just call this first part. I'm also going to call the radius of the circle A. A cosine omega t. Now, we don't just have our cosine omega t because there's also a length and the pendulum is moving along with the circle. So we can also describe this part that the pendulum is moving on as correspondent to the sine of that triangle. So we will also have L sine phi. Now our y coordinate is a little trickier. Since our coordinate axis begins in the middle of the circle, when it is up here at this point, it is going to be exactly negative y. So that is also going to correspond to a value that we need for our original y-axis is going to be negative a. And the way we can go about this is if we call it negative a sine omega t. And again, we also don't just have the circle moving, we have the pendulum attached to the circle. So that will give us the cosine correspondent to this angle that is being made. I should have said that I'd call that phi earlier, but I called it phi here, so that is correspondent to L cosine phi. And now that we have these, we can describe our x dot. Our x dot is going to be minus a omega sine omega t plus L phi dot cosine phi. And we do the same with our y dot. We have minus a omega cosine omega t plus L phi dot, and this becomes negative sine, so minus sine phi. And upon squaring these for x dot, we get a squared omega squared sine squared omega t plus L squared phi dot squared cosine squared phi minus 2 a L omega phi dot sine omega t cosine phi. And for our y dot, we get a squared omega squared cosine squared omega t plus L squared phi dot squared sine squared phi plus 2al omega phi dot. Should have probably put the dots there too. 2al omega phi dot cosine omega t sine phi. And now we sum them. So we have, these terms are easy. We have a squared omega squared, and then we have sine squared omega t plus cosine squared omega t plus L squared phi dot squared also times cosine squared phi plus sine squared phi plus 2al omega phi dot sine omega t cosine phi, and this first term is actually negative, minus sine omega t cosine phi dot plus cosine omega t sine phi. I said phi dot, my bad, I meant phi. And this can also just be written as our trigonometric identity, 2al omega phi dot sine of phi minus omega t. So we have a squared omega squared plus L squared phi dot squared plus 2al omega phi dot sine phi minus omega t. Now, using one of the theorems that we learned previously in one of the sections in this book, the time derivative of any separate function can just be omitted from the total Lagrangian because it's arbitrary. So it makes no difference to the equations of motion. Now, this term here is dependent on t phi dot, and it's also linear. So that's a dead giveaway that it is a total derivative. Now, how can we set it up as such? If I omit the 2al omega terms, right? And if I take the derivative with respect to time of cosine of phi minus omega t. Now I'm also going to make this negative because the derivative of cosine is negative sine, and if I make it negative, we get the result we want, which is just sine phi minus omega t. So, taking the derivative of this, I get sine phi minus omega t times phi dot minus omega t. Sorry, phi dot minus omega. And if I expand these terms, I'll have sine phi minus omega t times phi dot minus sine phi minus omega t omega. And this is exactly the term we want. So we can simply just rearrange for it. So if I rearrange for that term, sine phi minus omega t phi dot is equal to negative time derivative of cosine phi minus omega t plus omega sine phi minus omega t. And if I just multiply all of this again by my 2al omega, then we have exactly the term we needed up above. So now I can actually completely write my total Lagrangian. My total Lagrangian will consist of 1/2 m times a squared omega squared plus L squared phi dot squared plus omega squared AL, sorry, I should just write 2AL omega squared sine phi minus omega t. Now, I omitted this term completely because a time derivative of any function added to a Lagrangian does not impact the equations of motion whatsoever. And that thus becomes our kinetic energy for the system here. Now, working on our potential is minus mgy. So we have, it's t minus u. So minus u would be a plus because it's minus mgy. And our y term is minus a sine omega t plus L cosine phi. Minus a sine omega t plus L cosine phi. And again, all of this being multiplied by mg. Now here we also have another function that is just dependent on time, and it is just like adding a time derivative function to our Lagrangian, which we can also just omit. So our total Lagrangian simplified beautifully now becomes 1/2 m a squared omega squared plus L squared phi dot squared plus 2al omega squared sine phi minus omega t plus L, I should just write mg first, mgl cosine phi. And this is the beautiful result that is also given in Landau's.